So today we're going to dive into Chapter 13 and really break down the core principles of concrete foundation design right from the ground up.
All right, here's our game plan. We'll start by looking at the scope of Chapter 13, just so we're all clear on what it covers. Then we'll get into classifying the different types of foundations. After that, we'll hit the really critical design rules, apply them to a specific case for reinforcement, and even walk through a full calculation step by step. And finally, we'll wrap it all up with key takeaways. Let's get started.
So before we jump into the how-to, we really need to understand the what. What kinds of foundations does this chapter even apply to? Section 13.1 of the code lays this out perfectly, so that's our first stop. And let me tell you, the scope here is incredibly broad. Chapter 13 covers both non-pre-stressed and pre-stressed foundations, so pretty much everything you're going to run into. This includes all the shallow systems like strip footings under a wall or huge mat foundations under an entire building. And it also covers deep systems that use things like piles and caissons to get down to better soil. Basically, if you're designing a concrete foundation, this is where you begin.
Okay, so now that we know what the chapter covers, let's start classifying these systems. It turns out that all those foundation types we just mentioned, they all fall into one of two main families. And what separates them comes down to one simple thing: how they get their load into the ground.
The difference here is really fundamental. Shallow foundations, just like the name says, transfer the building's weight to the soil pretty close to the surface. Deep foundations, on the other hand, are what you use when that surface soil just isn't strong enough. They act kind of like stilts, punching right through those weak upper layers to transfer the load way down to stronger soil or rock deep underground. Let's look a little closer at shallow foundations. The one you pick really depends on the load. If you've got a continuous wall, you'll use a strip footing. For a single column, a simple isolated or pad footing is your standard choice. Now, if your columns are really close together, you might design a combined footing to support them both. And for really heavy structures, or when the soil's just not great, you might go with a mat foundation, which is basically one giant slab under the whole building. Now for deep systems. The real workhorses here are the piles themselves, these long, slender members that get driven or drilled way down into the ground. But a column almost never sits on just one pile. Instead, you'll have a group of them, and they're all connected at the top by a thick concrete slab we call a pile cap. The pile cap's job is absolutely critical. It takes that concentrated load from the column and spreads it out evenly across all the piles in the group. So, no matter if it's a deep or a shallow system, ACI 318 sets out some ground rules that are just non-negotiable. These are the core principles that make sure every foundation is safe and performs the way it's supposed to. This one sentence from the code, this is really the heart and soul of foundation design. It sets up the most basic rule of safety. Factored loads just means we take the expected loads, like dead and live loads, and multiply them by safety factors to account for any unknowns. And the rule is simple. The strength of our foundation has to be greater than those factored loads. It's that classic capacity versus demand relationship that drives all of structural engineering. And this brings up a hugely important point. We don't do structural design in a bubble. ACI 318 makes it explicit that our designs have to be based on solid principles of soil and rock mechanics. What that really means is that we have to work with geotechnical engineers. We need to make sure the ground itself can handle the load without settling too much, or worse, having a complete bearing capacity failure where the soil just gives way. Okay, so following these big principles often comes down to getting the small details just right. So let's shift gears from the general to the specific and look at a really common problem. How do you properly distribute the rebar in a rectangular footing? Because it's not square, the stresses aren't even, and the code has a specific rule to deal with this.
The key to this whole thing is a really simple ratio called beta. All it is the length of the long side of the footing divided by the length of the short side. So for a square footing, beta is 1. For any rectangular footing, it's going to be greater than 1. This little number is what we're going to plug into the code's formula. And here's the formula the code gives us. In this equation, gamma S represents the fraction or the percentage of the total reinforcement that has to be packed into a narrow band right down the center. And there's a good reason for this. The bending moment is way higher right under the column, and it fades out toward the edges. So this rule forces us to put more steel exactly where the stresses are the highest. Makes sense, right? Theory is one thing, but let's make this real. We're going to take that formula and apply it to a simple design problem so you can see exactly how it works in practice. Okay, so here's our setup. We've got a rectangular footing that's 4 meters long and 2 meters wide. And from our analysis, we know we need a total of 2,000 square millimeters of rebar running in that long direction.
The question is, where do we put it all? The whole calculation is just 3 simple steps. First up, we need to figure out that geometry ratio, beta. All right, step 1, calculate beta. We take the long side, 4 meters, and divide it by the short side, 2 meters. That gives us a nice, clean beta value of exactly 2.0. All this tells us is that our footing is twice as long as it is wide. Easy enough, right? Now that we have beta, we can move on to step 2, which is to find that reinforcement fraction using the ACI formula. For step 2, we calculate gamma S. The formula is 2 divided by the quantity beta plus 1. We just plug in our beta of 2, so that's 2 divided by, well, 2 plus 1, which is 3. 2 divided by 3 gives us about 0.667. This means 66.7%, or 2/3, of our total steel has to go in that central band. All right, we're at the final step. We have the fraction, so now we just have to figure out the actual area of steel that number represents. So for step 3, we take our total steel requirement, that's 2,000 square millimeters, and we multiply it by our fraction, 0.667. That gives us a final answer of 1,334 square millimeters. And here's the practical part. That much steel has to be placed within the central 2-meter wide band of the footing. The rest of it, the remaining 666 square millimeters, gets split up and placed evenly on either side of that zone. And just like that, our reinforcement is detailed exactly as the code requires. Okay, let's zoom back out from that calculation for a minute and quickly summarize the core principles we've covered. These are really the key things to keep in your head for any foundation design you work on. First, safety is everything. Always design for factored loads. Second, you have to know your system. The way a shallow foundation behaves is totally different from a deep one. Third, the details really do matter. Little provisions like the beta factor rule for rebar are in the code for a very good reason. And finally, and this is maybe the most important one, remember that ACI 318 is a framework, it's not a cookbook. You have to apply it using good engineering judgment and solid geotechnical information.